already waiting for 5 minutes. Maybe we should now start the webinar. Probably people will join in the next few minutes, and let's start so we keep on schedules. First of all, good morning, everyone, and welcome to today's EPICURE webinar on POP, Center of Excellence on Performance Metrics, a beginner guide with CoE, Scalasca, and CUBE. This is the third webinar of a five-session series in our webinar series on profiling, designed to guide you step by step through the key concepts and tools of parallel performance engineering. And thank you very much for attending, and we are delighted to welcome you to talk about profiling. Regarding our today presenters, Ilya is a senior HPC consultant at Jülich Supercomputing Center with over 8 years experience in supporting users of large HPC centers. He has been closely involved in the POP CoE, Civ GCS, and EPICURE projects at Jülich Supercomputing Center, providing hands-on support to researchers across diverse scientific domains. His primary focus is on helping users exploit HPC systems efficiently and improve the performance and scalability of their applications. Our other guest presenter is Mark, research scientist at Jülich Supercomputing Center since 2010, with a focus on performance tools in the context of the instrumentation and measurement framework SCoRP. As a part of projects like Mont Blanc, DeepSea, and POP, his focus has been support of application developers through a combination of user support, training, and performance analysis. Ilya and Mark, thank you very much for your availability to be with us in this webinar. For the attendees, just feel free to use the chat to put any question during the presentation to our presenters. We'll be monitoring it and ask the questions to Mark and Ilya as you put them, and of course in the end there will be an opportunity for questions and answers from them. Okay, during the session we just ask you to keep your microphone muted to prevent background noises, but feel free to turn it on to ask any question if you need it to. Okay, this session will be recorded and we'll have it access to it in the end. We'll provide a version of this webinar online. Thank you very much for attending. Ilya and Mark, the floor is yours. Okay, thank you. Oops.
Thank you, Antonio, for the very nice introduction. I'll start with the sharing. I assume you see my slides, so I'll start with the third webinar in the series, and this time it will be about POP, Center of Excellence, and its performance metrics. So basically, you can imagine you have a car and you would like to get some metrics about how your drive is going on. For example, which speed it is going on, how much fuel you're consuming, and so on. We would like to get very similar metrics for our parallel application. And this is kind of one of the goals of the POP Center of Excellence. And during this webinar, we will introduce POP CoE metrics and how you can get them with the scoRP, Scalasca, and CUBE. Let's first start with the introduction of POP CoE. POP stands for Performance Optimization and Productivity, and CoE stands for Center of Excellence. A Center of Excellence is a virtual organization, and multiple experts are joining this organization and provide different services. In this case, they're promoting best practices in parallel programming. And what kind of services POP can provide? They provide free services to help understand how application behaves at a parallel application behaves, and suggest if its behavior is not appropriate or for the certain HPC system, how you can improve it or modify it. And this is services are available across the different scientific fields, different HPC platforms and scales, and they're available for your HPC academic and industrial applications and users. Who are the partners? So this is a list of partners. This is a big team with experience in parallel performance analysis, in a lot of experience in tools and tuning and research and development background. And they have a really great experience, and they are keen to share it with you. So what was the ground why the POP was actually established? Because complexity of parallel systems and application is growing, and there is no beginners I usually don't understand how well application is running at the system, and so they need some metric to understand how it runs and if it runs well or there are some issues. And also they need some guidance how they can improve and achieve like best efficiency on this particular system, or like get a reduced time to solution or energy consumption. So this is basically is the motivation why POP was established, and now it is a third iteration of POP. And POP is providing guidance on mainly on MPI and OpenMP, but also in for GPUs like OpenACC, OpenCL, CUDE, and so on. So you name it, many parallel paradigms are supported, and we are welcome to apply for the services. So now I'll shortly talk about general process. So to apply for the POP services, you need to go to the website, this popcoe-coe.eu. It is marked here. There is a certain time frame when you can apply, because POP 3 is running until end of this year, but there might be a continuation after that. How you can apply, you go to the website, click on request service, and you fill a small questionnaire. This is an example of the questionnaire. You specify what kind of application is it, what kind of scientific domain, is it MPI, OpenMP, what kind of parallel programming language do you use, C, C++, Python, or Fortran, or something more exotic. Once you applied, there is a selection assignment process, because there are multiple partners, and any of the partners can help you. There will be a consortium meeting, and they will decide who can actually provide you help. It might be people or user support from the system you apply for, or they can be from a different system. Once it's assigned, supporters will help you to install some tools. It can be on a specific system or locally, on a your HPC system or on your local machine. And then they will help you to gather data, help basically. It's also mentioned that it interactively. So this is cooperative process. The user and support have to collaborate and work together, mutually help themselves. So first they will help to install tools, then gather data, analyze and report. And in the report, they will provide this kind of metrics which I mentioned. They are called POP metrics, and we are going to focus on them and discuss how they can be computed. These metrics are called efficiencies. Please don't confuse it. Like in HPC, we also have an efficiency and speed up. Please don't confuse with them. They're quite different from what is like a typical efficiency or speed up of applications. They have a relation, but they're not one-to-one mapping to each other. So POP developed a methodology for analysis of parallel codes to provide a quantitative, so basically it's a metric way of measuring relative impact of the different factors inherent in parallelization. So basically in the POP, we will try to understand which factor prevents you to, let's say, to scale or what is inefficient on your application. And then they provide the certain metrics. It's not a single metric, it's a set of metrics, and it's also hierarchy of metrics. And each metric reflects a common cause of inefficiency in the parallel programs. We'll discuss all these metrics in a second. So they are represented from 0 to 1. So 0 is the best, is the worst value, and 1 is the best ideal case. And usually out of experience that values are lower than 0.8 indicate some performance issues. Why do you need them? What are the benefits for the POP efficiency? It's easy to identify which characteristic of the code contribute to inefficiency. It might be communication, it might be load imbalance, it might be computation. So you would like to know what exactly contributes to this. And of course, it allows to compare parallel performance. You can do like a reference run, but then you do a modification in your application, and then it is easily to compare. For example, if your load balance has changed, or if the communication has changed or improved. This is quite interesting and quite easy to compare. They're relatively easy to compute. Mark will demonstrate how one can compute them. It's basically can be done in automatic standards way. Usually single run is sufficient for basic efficiencies, but there are multiple efficiencies, and usually single run is not sufficient for the more sophisticated metrics. Mark will also demonstrate how to do a set of measurements to get a full spectrum of metrics for this particular case, which he's going to present. And as the values are from 0 to 1, it's relatively easy to understand if you are good or bad. And you can apply these metrics to different parallel paradigms like MPI, OpenMP, and also combination MPI plus 6, MPI plus OpenMP, MPI plus GPU, parallel models, and so on. Here is depicted an efficiency hierarchy. So I must admit this is basic. This wasn't implemented in the POP version 1, but then it's still valid. But the metrics and hierarchy are developed and changing with the time. For example, if we consider this. This is quite basic, but if we want to extend it for GPUs or pthreads, you might OpenMP, you might be want to get slightly different metrics. They're all available on the website. What I want to cover, all these basics metrics. If you understand them, you understand how basically POP metrics are calculated and what hides behind this. So here basically you can see that's the hierarchy, and we will read it from top to bottom. So the global efficiency, global efficiency consists of two main subcomponents: parallel efficiency and computation efficiency, whereas parallel efficiency constitutes out of these two: load balance efficiency and communication efficiency. And communication efficiency consists of serialization and transfer efficiency, and so on. So basically, this is a hierarchy, and they have a sub-components, and we will cover all of them. First, let's start with the global efficiency. Global efficiency describes overall quality of the parallelization, and it consists of two components. Parallel efficiency, which describes overheads imposed by the parallel nature of a code. So how efficiently your application is parallelized. Second component is the computation efficiency, which describes indicates if the poor scaling of computation with increasing number of processes. And the global efficiency is computed by a multiplication of parallel efficiency, how good is your application is parallelized, and by computation efficiency, how good your application scales in the sense of computation. Now let's go further and describe how you can compute parallel efficiency. And parallel efficiency describes how well your execution in the code in parallel, and it consists of two components. One is the load balance efficiency, which describes distribution of computational work across processes. How good are they balanced in the computation. And the second component is the communication efficiency, which describes communication across processes. And again, this it's very simple to compute parallel efficiency. We need to compute multiply a load balance efficiency with the communication efficiency. But to identify load balance efficiency, I would need to go a little bit more to the detail and explain the formulas. And here I have some examples. So load balance efficiency reflects how well the distribution of work to processes is done. And basically, you can see in the formula that the load balance efficiency is the ratio between average and maximum time a process spends in computation. Let's consider the first example here. So we have three processes. This is a timeline reading from left to right. Process 0, process 1, process 2, and in blue is the computation phase, and the red is the communication. So in general, we don't want to communicate. We just want to compute. Communication is kind of considered as an overhead. And to calculate load balance efficiency, what we need to do, we first compute average computation time across all processes. Then we know this component, and then we compute maximum computation time. And but here they are more or less the same. So we'll have average and max are the same. That's why in this case, we'll get load balance efficiency equal to 1. But if we have some imbalance between computation average and max, we will see that metric will go down. So here, for example, we'll have 0.7 cent. And in this sense, we can quantify how good is our load balance. Second component is the communication efficiency. And this is component reflects the loss of efficiency by communication. And here it is computed by SM relation. We compute it per process and then find the max. So per process, we compute computation time divided by the total runtime. We compute it for each process, and then out of the set of computations, we will find the max. For example, here we again see computation and communication, and in the table you can see the relation here for the process 2 will have 1 second in computation, 2 in communication, and so on. So for all processes, and here then we can basically identify communication efficiency for each process, and out of them we'll find the max. In this case, this is for this process. This will be the max, and we'll use it for communication efficiency. basically you can see that we are taking the best case. So it means that if communication efficient, if the best case is already bad, then you should really take and have a look at your communication pattern or communication in your application. So that's the reason why in this model it was taken the best case, because in worst case maybe a single process is spending quite a lot of time in the communication, but then it would be the metrics would be skewed, and we would like to consider best case. And as we already mentioned, there are two subcomponents which are influencing communication efficiency, and those are serialization and transfer efficiency. Serialization efficiency, it's efficiency due to the waiting time within communications, and transfer efficiency and efficiency due to data transfer. So, and the communication efficiency can be also computed as a serialization efficiency multiplied by transfer efficiency. How to compute serialization efficiency, and what is serialization efficiency? Serialization efficiency describes the loss of efficiency due to the dependency among processes, where dependencies can be observed as a waiting time in MPI calls. From the second webinar, we mentioned, for example, late senders, where receiver was posted before the send, MPI send, and there is a waiting time. So this and the kind of dependency in your application, and this we would like to detect and quantify as for serialization efficiency. For this, we also imagine that we have a ideal network. So basically transfer from A to B doesn't take any time. The transfer can happen instantaneously. And for this, with this imaginary network, we can compute serialization efficiency as a relation of computation time on ideal network divided by total runtime on ideal network. And out of this, we'll find max across all processes. Here again, we have two processes. Blue is computation, and red is communication. And you can already see this is our receiver, and this is our sender. This is typical late sender, what was mentioned by Michael last time. So basically, this is a waiting time because receiver is just waiting to send to start. So we'll analyze all our traces, all our events, and indicate what is the waiting time and remove the actual transfer time. So in this case, this would be transfer time, and this is waiting time. And the same as here. Here is the waiting time, and here is the transfer time. To model the ideal network, we basically remove everything what is related to the actual transfer, and then at the end we'll get something like this. The model will only have a computation and some waiting time due to dependencies. And based on this, we can compute our transfer efficiency. This is like, serialization efficiency. Sorry, so basically, what we need to we have a computation time on ideal network, which is like in this case it will be 4 plus 3. For this case, it is 7, or 6 for the process 0. 2 plus 4, it's 6. And total runtime on ideal network, it will be this full, like 4 plus 3 plus 1, it will be 8. And we will have to select the max across all of them. And in this case, it will be 7 divided by 8 for this process, and it will be equal, efficiency will be equal 0.88. It again, we'll consider the best case. If the best case is bad, you should really look into your serialization. And very similar to this model, we can also consider transfer efficiency. So how much efficiency lost due to actual data transfer. And to compute this, we'll use the following formula. We'll divide total runtime on ideal network divided by actual total runtime. Total runtime on ideal network is basically this runtime. We assume that in all processes we have a similar runtime. And in this case, it would be total runtime on ideal network 4 plus 3 plus 1. It would be 8. And actual total runtime, it would be all this. 4 plus 2 plus 3 plus 3, it would be 12, and then it will be a transfer efficiency. What we lost because we were sending maybe too much data. So in this way, you can identify serialization and transfer efficiency. Now let's go to the computation efficiency. And computation efficiency describes efficiency of computational load of application at scale. In this case, we are considering strong scaling. I remind the strong scaling, the problem is fixed, but the amount of processes is increasing at scale. And computation efficiency of a linear scaling application should be similar if we have something like very good scaling application. So basically amount of work supposed to stay the same, but we only divide this work across processes. So and then the computation efficiency would be equal computation time on process 1 divided by computation time on n processes, some aggregated value. So that's why if it's very good implemented, that it should be equal to 1. Of course, it might be a little bit, you can also get something like superlinear speed up due to caching or other effects. You can also see it in computation efficiency too. And computation efficiency constitutes of two additional efficiencies called computation efficiency, instruction efficiency, and instruction per cycle efficiency. So instruction efficiency, it describes work division over additional processes because you at scale you use more processes, and again in theory amount of instructions, amount of work, it's basically describes amount of work should stay the same, but if this division causes additional work, then you will have a more instruction efficiency. And we also have to identify speed of processing the instructions. For this, we'll use IPC or instruction per cycle efficiency. Using additional processes leads to contention for shared resources quantified with this particular efficiency. So, and the communication efficiency is the product of these two instruction and IPC efficiencies. Now I would like to go briefly through a short success story. This was analyzed in the POP3. This application is a spec FEM3D, was executed on Leonardo Booster, and it represents a strong scaling. It is implemented in Fortran 90, MPI plus CUDA, and we use one rank per GPU. And in this case, we'll focus on an iterative solver. In POP, it's called focus of analysis. And the conclusion is basically that we have a good scaling up to 256 GPUs, but with at scale up, it doesn't scale well anymore due to insufficient overlap of MPI communication with CUDA kernels. So here you can see on the graph how is this like strong scaling. Weak scaling is below. It's hard to see, but weak scaling is really good, but the strong scaling is also very close to ideal. So this dotted one is ideal, but at the scale of 512 GPUs, the strong scaling is degrading. And it also was analyzed with the pop metrics. Here we can see the different metrics, each row, and here's a different test. Here, test of this 8 MPI GPU ranks, 64, 128, 256. All values are relatively good, more than 88 or 85. So 85 is a quite good efficiency. But if you go to the at scale 512, we already see that significant degradation. And in this case, it is due to orchestration efficiencies or overlap between MPI and CUDA kernels are not so good. As I already mentioned, there are multiple metrics depending on models you are using, and they're evolving together with the POP. On the graph, you can also see different bars. First bar is representing GPU compute time, and gray is the idle time, and second is how CPU is behaving. Yellow is the CUDA synchronization, and purple is the MPI communication. So basically, we can see that at scale, GPU compute time is still not significant, so idle time is not big. But at scale of 512 GPUs, that we have a significant increase of idle time and also significant increase in CPU computation, and also in this orange, which is a CUDA sync and MPI communication point-to-point. Yeah, so here's a little bit more information about this application. You can see the cube file here, and also you can see the topology, how CUDA, how GPUs are. This is, in this case, we can see time overhead in CUDA. In GPU. So, and we can also see the 2D domain. So we see how GPUs are loaded in this for particular function, and many kernels are well balanced here, but on the boundaries there is some more load. And only 4 GPUs handle seismogram receivers, so they are depicted here. And only one GPU executed a compute at sources kernel. This is here. And basically, here's a little bit more details about this. This compute at source kernel executed on a single GPU only, but it's rather short, however, results in all other GPUs having very long synchronization times in following transfer boundary function. So basically, you can see here this process is working, and the others are more or less idling and waiting for the in synchronization routine. So, and over 2/3 of CUDA sync time and over 30 time of total CPU time. So basically, the POP metrics helped us to identify this, and also indicated that the orchestration efficiency is not very good at this scale, and maybe one needs to restructure application to distribute this compute at source kernel, for example, across other GPUs. Yeah, this is basically demonstration. There are many other functions available, and also POP metrics are, many other POP metrics are available. They are available on the website, and Mark now will describe how the POP metrics can be achieved with the CoE, Scalasca, and CUBE.
Hello, everyone. Can everyone see my screen?
Yes.
Okay. So since Ilya described what kind of metrics we are kind of getting, we are now basically seeing the process of how to get there with CoE and technically with CoE, Scalasca CUBE, our general tool environment. And this mainly depends on two topics. One, what kind of metrics are available from the data you have measured, and then the procedure to actually get there. So it hinted at it that the basic set of metrics are basically always available because they are just calculated from the standard data that's available. But something like the computational elements like IPC and instruction information require hardware counters. So you have to measure with them specifically to get this information. And for the MPI serialization and transfer efficiency, we need a tracing run with Scalasca because this is information where we require the time dimension of a trace event stream to calculate it versus the information we are getting out the summary information of a profiling measurement. And if you're looking at something like GPU measurements, you have to see the GPU device side activities to get GPU metrics. So depending on what paradigms you are measuring, you have to make sure that the required information is in your in the measurements that you have available for calculation. So the procedure generally consists of two steps. Once you measure the required data and merge the data if necessary, if you have to do multiple measurements. And the second step is then to use CUBE to calculate the metrics, where we have two options to go there. On the one hand, we have the command line tool CubePop metrics, which does basically the output on the command line interface. And we have a plugin for the CUBE GUI, the top advisor panel, basically where the same information is calculated on the GUI level. And when we are now looking at the process, Scalasca offers a convenience tool with a multi-run feature that allows to do multiple measurements easily and merge the data if necessary. And that's basically where we want to start what we want to show here. The Scalasca multi-run is very lightweight and very specific to our Scalasca execution. So we don't want to replicate the bigger systems like Droop, where we have very complex systems with parameter spaces that we can run. So we have relatively simple setup where we have a set of configurations limited to CoE and Scalasca variables. And then we have the option to run these configurations multiple times. The configuration, the use case is to have a specific set of parameters set up for your measurement run that is repeatable and so that you want to use in any case. And the advantage of repetitions is to get basically a statistical stability. Depending on your system and where you're running out, you will have more or less system noise through shared system resources and getting a bit of averaging out of your measurements can improve your the quality of your values. And in this context, where we are looking at specifically at the pop metrics, this is a use case basically for this multi-run feature where we defined specific presets that we can choose, which is a configuration that we know, okay, that gets us the data that we are looking for. If you're looking at such a configuration file, we have basically two different sections. One is the global section of variables where we have CoE variables, for example. Since you had the prior webinar where Michael presented some of the elements, you should be familiar with some of the variables that we are seeing. So basically the controlling variables like enable profiling or tracing or adding a filter file. So in the global section, you set variables that are used by both runs unless they are changed. And they are also state basically variables that cannot be used in the general environment outside of this configuration file, simply for consistency checking. And then you have multiple sections for singular run configurations where you have specific setup for example, a run with profiling and puppy counters. In this case, the classic set of instruction cycles and resource stalled. And then run with Scalasca, where we deactivate the profiling and just setting setting up the run for the tracing. In general, otherwise, it's the syntax of key value pairs of the variables and nothing magical behind it. And if you successfully ran this multi-run, you get a measurement directory that contains, for one, the measurement configuration, but also the set of singular measurements that consists the whole multi-run measurement. In this case, for this example, we had 3 configurations and each were repeated 2 times. We get 6 measurements. This is generated through the measurement run via scan. And then in the second step, we post-process this information into an aggregated result, which is done by our tool Square. This is basically the base information about the multi-run. And since this is a bit of a dry information, we're doing now a live demo with this on our system. In this case, I'm using Eureka, but since it's a standard example of BTMZ, this can be run basically anywhere. It's a standard tool we are using for demonstrations and hands-on demonstrations. In this case, we are assuming basically that you already have configured your measurement and application to run with CoE and Scalasca and can go then to do a multi-run measurement for this use case. So we're assuming you know you have to have a filter file for this application and set the memory requirements for your Scalasca measurement. But otherwise, we are going now from doing a simple singular run of Scalasca to a run of with a pop preset, which is just a minus dash p and pop, and then your standard run parameters. We have a few, as mentioned, variables in this job script, also in the general environment, but because they don't appear in the preset configuration, there will be not a conflict. So if you are using this job script and can run this on our system, let's see. Oh, it's directly starting, so that's nice. While we are waiting for it to complete, we can have a look at the help output from scan and basically see our options that we have here. So we are using right now the -p preset, which is using the pop one. But we could add in principle the number of repetitions we want to have. By default, we're just doing 1, but you can combine it with the number of runs. The -m option is for a generic config file, which follows the same format, but isn't predefined. -l offers you the option to list all the stored presets. And -d allows you to basically have a dry run check of your configuration file if it's valid and can be used as a configuration. If you're checking the -l, currently it's basically just the pop preset. There's also a variant of pop with additional information, but we're using the pop one, and it lists also the file location where it's stored, and it's basically a similar set of settings as I showed on the slides, where we have 2 runs. One is the Scalasca tracing run, one is the profiling run with puppy counters. And so just some variables set in the general environment that we generally do not want to use to be changed. For example, some that would break the measurement if you have different output names that aren't expected, or some elements that like memory recordings that would increase your overhead without adding for this specific metrics. So they are added basically to prevent you from using them in the environment. As long as you have write access to your directory where it's installed, you can add additional presets or change them to your needs and get them modified. So the job runs through. So what we are getting out of it is a measurement directory with a name convention of Scalasca, where we have basically the name of the application, then the number of processes, number of threads, and that we use the preset pop with 2 configurations. And if you're looking in this, you're seeing something similar to the output. This is just the from the run, we have just 2 configurations and no repetitions, so we are getting 2 measurements. And the Scalasca config file is that configuration that we ran with, which includes the basic settings we got from the preset, but also includes the settings we inherited from the job script, also from the environment that we set manually. So for repeatability, these settings are basically stored there and can be reused. And if we are looking at the cube files we find here, we currently have a profile measurement and a scout cubex from the trace measurement. Since we cost-wise deactivated tracing and profiling, we just get 1 of each. And now the next step is basically to remap these and combine them into 1 measurement. And for this, we are using Square. And by default, you just have to use the Square in its default settings on the directory, and it will recognize that this is a multi-run measurement directory and do the necessary steps of first merging the files and then remapping the result. And as you just saw, it will automatically start the GUI, but we get to that since we're still on the command line. I want to look at what we got in the output of the. Now we have additional cube files. We first get aggregated cube profile and scout measurements. This is in this instance, since we just did 1 repetition, they are the same as the singular instances from the singular runs. But if you, in case you would have runs with repetitions like 2 or 3, these would be the aggregated, respectively, scout and profiles. And the next step is the combination of scout plus profile, and then the remapping steps that Michael probably mentioned in the last webinar to get the full set of metrics with the remapped program. And just to get into the weeds, if you're looking at the help output from Square, you have the option to change the aggregation method that is used for the aggregation. By default, it's an average. So if you take 2 cube files and you average them, you basically get the classic elements of statistically analysis to average your values per entry, basically. Then the other method of aggregating cube files is merge, which takes the multiple cube files, but only takes the new elements from a second file to add them to the other file. So you get basically, if you're joining a profile and a cube file and a trace measurement, you are getting the timing information for your whole year of call tree from the scout measurement. But since the profile adds a new counter measurement, it adds these counter metrics to the profile and merges them together. This way we get the better timing information with less overhead, and we get both information in 1 measurement. And since we are now in the state where we have a fully aggregated result, we now can calculate our metrics. Staying on the command line for now, we are looking at CUBE pop metrics. We are choosing an analyst type, and this for this is a hybrid program. We're choosing the default metric for that, and then the now merged trace plus summary cube measurement. As you mentioned, normally you want to probably choose a focus of analysis, and you can specify the regions that you want to look at. But otherwise, you are getting basically the output for the default whole measurement, and you're getting the set of metrics, which includes now the classic set of that they described, plus the serialization and transfer efficiency we are getting from the tracing, as well as the IPC and instructions from the profiling measurement. And if you're looking at the additional information you see here, you're also getting information for the threading, which are on similar lines as the computation balance and the communication efficiency on the process side. We also have metrics for GPU side, but since it has no GPU calculations in it, it doesn't calculate them. They're not available. Similar thing for I/O metrics, unless you specifically measure POSIX I/O time or MP-I/O time, you don't get additional information here. But that shows, depending on what kind of measurement you have, what your application provides in terms of paradigms, you will get different information. So since this is basically the way to do this on the command line, this is primarily a good use case if you are running the metrics on multiple cube files and then do some tabular sheets of it. It's easy to extract the information here. But you also can do this on the GUI side of things. So this is a classic view of the cube side. And since you're seeing the PAPI counter as well as metrics from the critical path and delay costs, you basically see that you have a successfully merged trace summary measurement. And now we can basically look at the optimizer panel and the general tab and calculate the hybrid metrics for the whole application. Or if you want to choose, you now can select various set of sub-elements of the call tree and then calculate the metrics for this set. And you basically get listed the what your focus of analysis is. That's the great feature of when doing this in the GUI, is that you have the ability to select varied and very specific call tree selection very easily, depending on your understanding of the code, what's your main application or what's the iteration phase you want to specifically look at, and select the information based on that. Otherwise, the information that you get out of it from the calculation is very the same as on the command line, because the calculations happens in the library behind it, which are doing the same information. Something we are looking at in the future is to export this selection and then use this selection on the command line for easy of use for reuse, basically. And the GPU side of things is probably the most in development still, because there are, in the current project of POP, we are still looking at the various elements, how to combine the metrics with different sets of paradigms in your application. So I would say that's for that, and we can go back to the side of the slides and return. Just when you look at the slides later, there are a few slides basically from the demo which contain the metrics for this example, but otherwise they're doing the same thing. And just to round it out, if you're looking at the broader context of POP, there are various tools that provide this information. You have our CoE Scalasca CUBE tool environment that's used here, but you have also the BSC tools where there are various ways to calculate the metrics on tool from the University of Aachen and also Macau allows you to calculate the metrics. Which one you choose most of the time depends on which tool chain you're basically familiar with, but also the tool chains have different features and focuses. So depending on what kind of analysis you're looking for, you might look at different tool options there. And if you want to know more information about the whole topic of pop metrics and their tools, the webpage of popcue.eu has a lot of learning materials, definitions of our metrics, and also additional webinars. I think we are currently in process updating the list of metrics and the documentation features. So looking in future there, that might be helpful to get new information. Yeah, and I think that's from our side. If you have any questions, we're happy to answer.
Okay, thank you very much, Mark and Ilya. And now for you, there were some questions in the chat that Mark already answered. But is there?
Yeah, just for completeness, what I answered. Also, there's a POP project, POP 4, in the process of being hopefully accepted. So if it's accepted, it will continue basically in January, so continuously. And as mentioned, the metrics, depending on what you get, you're getting metrics for the process sides of things, but also the threaded side of things, or in case of GPU applications, also for the GPUs.
Okay. Well, if there is no question, I have one question. Either EPICURE, either POP, they both provide support to user applications. I think the main question many people may be asking, which one should I use for my concrete case? When should we ask help from EPICURE? When should we ask help from POP? What are the conditions? And how can we do it for any of the projects?
Yeah, I can take this question. So basically, there is a lot of common versus POP and EPICURE, but there is also a difference. Common that we both provide performance analysis and optimization hints for your HPC applications. Difference for EPICURE that we provide more, for example, debugging of the application, porting of the application from CPU to GPU, or vice versa. So the spectrum of services is much broader, and it is also possible to get some metrics if they who providing services are aware of POP metrics. It is also possible, but in general, to keep in mind that if you want to do some modification in your application, that EPICURE is more suited rather than POP. Because in POP it's analysis, and at the end you'll get a short report where you'll be guided how you can potentially improve your application.
But in the end, we can get support from both.
Yeah, absolutely. Like no one prevents to apply for both and get both of the two words.
Okay, thank you very much, Ilya, for updating us. I think Commune is typing, but communist. Sorry, comment. You were asking something. Maybe you can make it here. I think I was being told that you have questions in the chat, but I think we have answered them all. Just for at least I don't see questions unanswered in the chat. Any other question? Okay, if there are no further questions, I want to thank you again to Ilya and Mark for this very thorough presentation and enlightening presentation. I think we have all learned a lot more on CoE tools and how the Euro HPC ecosystems can interconnect and benefit all of us. So just remind you that is a series of webinars on profiling and optimization. I start to have noise in the neighborhood, sorry for that. So this is, we still have 2 more webinars on this topic, so feel free or join us for the next ones. And as Paul is telling, please give us some feedback on these webinars. Paul has put the survey link in the chat, so please take a few minutes to give your feedback. It is very important for us and for us to keep this working and working well, we hope. Okay, so thank you very much. If you need some more information on EPICURE, you may follow us on the social networks and on the website, and the teams from both projects will share you or guide you on which the best platform or the best project to support you. I think it is not for not having support that we don't do very good and optimize our code. So thank you very much for attending and see you next week. Next week, no, in the beginning of July. I think next week most of us will be on ISC in Hamburg. So after ISC, we'll return to the webinars. Thank you very much.
Thank you. Bye bye.
Thanks. Bye bye.